Hello guys, welcome again. So today we are going to start the next article, that is the gamma and exponential distribution. We are not going to see that beta distribution. Of course, they are on the same line, but beta distribution, then log normal distribution, Weibull distribution, all these things that is in the next course of statistics. And that's why from this article, we are going to see only gamma and the exponential distribution and the relationship and how it is related with the Poisson distribution with some examples. So that's what we are going to see over here. Also, the normal application of the binomial, that is very easy. So that's why I think you can do that one by your own. So let me just start with this one. So gamma and the exponential distribution. So first of all, let me let you know what we mean by the gamma and the exponential distribution. Let me share my screen. If I share my screen, you can see here that density function is required. Although the normal distribution can be used to solve many problems in engineering and science, there are still numerous situations that require different types of density function, and two separate type of density function. They are the gamma function as well as the exponential function. Look at the gamma distribution and the exponential distribution, which we are going to see now. It turns out that the exponential distribution is a special case of gamma distribution. Please keep this thing in mind, because in gamma distribution, this is the definition of gamma function. You can see over here. So in gamma distribution, if you take, suppose your alpha is equal to 1, so in that case, the gamma distribution is converted in terms of the exponential distribution. So the other way around, I would say that exponential distribution is just the particular case of the gamma distribution. Both find a large number of applications. The exponential and the gamma distribution play an important role in both King theory and the reliability problems. Time between arrivals at service facilities and the time to failure of component parts and electrical system often are nicely modeled by the exponential distribution. Please keep this thing in mind. This is really very, very important thing, that this is the application of exponential distribution. Again, I repeat, that exponential and gamma distribution, they have plenty of applications in King theory and the reliability problems. Time between arrivals at service facilities and time to failure to component parts and electrical systems often are nicely modeled by the exponential distribution. The relationship between the gamma and the exponential distribution, the gamma allows the gamma to be used in similar types of problems. Right, and more detail we are going to see when we take the examples and like this. Let me start with gamma distribution. You can see over here, guys, this is the gamma function. Before starting the distribution, I just would like to go for gamma function. So my gamma function is defined by gamma of alpha. This is the symbol. Gamma of alpha is equal to integration 0 to infinity. I usually write exponential function first, e to the power negative x and x to the power alpha minus 1 dx, alpha greater than 0. So gamma function is defined like this: gamma alpha equal to e to the power x and x to the power alpha minus 1. Whatever exponent you have, this alpha stands over here. Suppose this alpha equal to 1 by 2, then that is the value of gamma 1 by 2. Alpha equal to 3, gamma 1, gamma 3, something like this, right? Here it says alpha greater than 0. That means you can take any value, 1 by 2, 1 by 3, 1 by 5, any value greater than 0. There are some properties of gamma functions that you can write. Suppose gamma of n. So gamma of n can be written as n minus 1 times n minus 2 times n minus 3 times ... up to finally 1 and gamma of 1. So this n minus 1, n minus 2 up to 1, that is nothing but n minus 1 factorial. Am I right? So gamma n is n minus 1 factorial and gamma 1, something like this. So just keep in mind this thing, that gamma n is equal to this one. That's really very easy to prove also. Suppose somebody says that gamma alpha, this one, gamma alpha is equal to, suppose somebody says that how can you come to this conclusion that gamma n equal to n into n minus 1, n minus 2 up to 1 and gamma 1. Okay. Then keep in mind this thing, that gamma 1 is always 1. So it is simply gamma n equal to n minus 1 factorial. Just keep this thing in mind. Gamma n equal to n minus 1 factorial, because gamma 1 is 1. I'll let you know. If you use the integration by parts, it's really very easy to prove this one. I am not going to prove this one, but I can give you a little hint because nobody's going to ask you the proof. But you can use integration by parts over here in the gamma function. Gamma alpha equal to, this is the exponential function. If you use by parts, means LIATE, exponential function. L stands for logarithmic, I for inverse, LIA, A for arithmetic function, T for trigonometric functions, and E for exponential function. If you use this LIATE rule, and whatever comes first, that is your U, and other function is your V. So U into V rule, right? Integration by parts means U into V rules. So if you take, suppose here, this e to the power negative x, that is my U, this is my U e to the power negative x, and x to the power alpha minus 1, that is my V. So we are taking, what is integration by parts? We are taking derivative of first function and U, and integration of second minus under the sign of integral. So look at over here. First of all, my U function as it is. So my U e to the power negative x as it is, and then integration of second function, x to the power negative alpha minus 1. I think, I'm sorry, function is x to the power alpha minus 1, right? So x to the power alpha minus 1 and V to e to the power negative x, because V stands later, an exponential function that is at the last. So that is my V. So if I take U as it is and integration of e to the power negative x, so U as it is, x to the power alpha minus 1, integration e to the power negative x divided by negative 1. So that can be written like this. Improper integral, of course, you can write like this, or you can write 0 to b and limit b tends to infinity like this. And then the derivative of my U, derivative of U is alpha minus 1, x to the power alpha minus 2, and derivative of x is 1. And integration again of V, that is this one. So you ended up, because if you take this one, this will be just 0 if you work on it, and alpha minus 1 constant, just pull it out of the integral sign. So alpha minus 1, 0 to 2, x to the power alpha minus 1, e to the power negative x dx. You can see here alpha is there and I'm getting alpha minus 1. N is there, I'm getting n minus 1 over here. Same way, if you use the integration by parts over here, by parts method here, U into V rule, this is my V, exponential function always V, and other function is my U. If you use that rule, again, you're going to get one more term, n minus 2, and integration 0 to infinity, x to the power alpha minus 3 to the power negative x dx, and so on. So by the induction method, you can say that gamma n equal to n minus 1, n minus 2, dot, 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 up to 1, and gamma 1. Okay, so gamma alpha is equal to, or gamma n equal to n minus 1 times gamma n minus 1. N minus 1 times gamma n minus 1, right? Or gamma n minus 1 is again n minus 2 times gamma n minus 2. Gamma n minus 2 is n minus 3 times gamma n minus 3. So ultimately, we are getting the same thing. Okay, so that is the first property. Second property is gamma n, as I told you, that is equal always n minus 1 factorial, because I told you gamma 1 is simply 1. So n 1, 2, 3 up to n minus 1. So it is n minus 1 factorial, very obvious from the first one, case A. Gamma 1 equal to 1, very easy to prove if you plug alpha equal to 1 over here. So 1 minus 1 is simply 0. X to the power 0 is 1. E to the power negative x, integration e to the power negative x, and negative sign. Okay, and then 0 to infinity, you're going to get that is equal to 1. So that is also very easy to prove. So gamma half is equal to square root of pi. Again, the same type of things, gamma half is equal to square root of pi. So if you take alpha equal to half, then here it is x to the power negative half and e to the power negative x dx. Again, you into V rule and you will get gamma half is equal to square root of pi. Okay, guys, then after we are going to see the gamma distribution. Now, gamma function is done. Now we are going to see gamma distribution. Gamma distribution can be defined in the form of alpha and beta. So my gamma, or you can say density function f x alpha beta. So continuous random variable x is there. As a gamma distribution, this continuous random variable x has a gamma distribution with parameter alpha and beta. If it is defined in the form of 1 over beta to the power alpha gamma alpha, and x to the power alpha minus 1 e to the power negative beta, x by beta, x greater than 0, otherwise it is 0. And please keep in mind this thing that alpha and beta both are positive, strictly positive. And you can see over here, if you take alpha equal to 1 here, in that case, it is 1 over beta. Gamma 1 is simply 1, no need to write. X to the power alpha is 1, so 1 minus 1 is 0. X to the power 0 is 1, no need to write. So this term will disappear. This term will disappear. And e to the power, then negative x by b. negative x by b. This is the function of alpha and beta with different values of alpha, and beta is fixed. Suppose beta is equal to 1, alpha equal to 1, 2, 3, 1, 2, 4, something like this. So you have this type of this graph and this graph. These are the graphs of gamma function. Anyway, and as I told you that exponential function is the particular case of gamma function by taking alpha equal to 1. So if you take alpha equal to 1, no need to write. X is the random variable, continuous random variable, of course, and that's why we have a density function f, and there is 1 over beta e to the power negative x by beta. So if you take alpha equal to 1 over here, you're going to get this formula or this density function. Once you have the density function, then naturally one can talk about the mean and the variance of the gamma distribution, because we already talked about the gamma distribution. So now what is the mean and variance? Is gamma distribution, and naturally same way we have over here the exponential distribution. So mean and variance of the gamma distribution is nu is the mean equal to alpha times beta. Mostly alpha and beta values will be provided to you over here in this chapter, but not always the case. Okay, that we'll see maybe in the next chapters, chapter 8, 9, something like that. So mean and variance of the gamma distribution, nu equal to alpha beta and sigma square, variance is alpha beta square. So mean is this one and variance is alpha beta square for gamma distribution. And you know that alpha is equal to 1 in gamma for the exponential distribution. So if you take alpha equal to 1, you're going to get nu equal to beta, and alpha equal to 1, sigma square equal to beta square. That is the very obvious for the exponential distribution. And this has some relation with the Poisson distribution. That is very important. Again, no one is going to ask you this thing, but please keep this thing in mind that Poisson distribution, that is, we learned in the last chapter, and that was the discrete probability distribution. Right now, we are doing the continuous probability distribution, in which we went over different type of distributions like normal distribution, uniform distribution, normal distribution, and then after you can see over here right now the gamma distribution, exponential distribution. So this one is actually nothing but the connection between the continuous random variable and the discrete random variable, because Poisson process we have seen that is for the discrete. That's a discrete process. So sometimes your examples should be like this. It could be something like this. It's a combination of discrete and continuous random variables. So please keep this thing in mind. And I don't want to go through all these things. You can take your time and try to go through this one. But the most important thing just I would like to mention is the most important application of the exponential distribution are situations where the Poisson process applies, right? So exponential distribution application in which the Poisson process again, the discrete probability distribution process is being applied over here. The readers, and another thing is, we always recall that the Poisson distribution, whatever we learned in the last chapter, there is a discrete distribution, and the Poisson distribution is used to compute the probability of a specific number of events during a particular period of time or span of time, right? Poisson distribution, that was just for some specific time or time of span of time or some specific area. That's what we have seen in the last chapter. In many applications, the time period or span of the space is the random variable. Now look at it. That was not the case at that time, right? We just decided about some fixed time, but sometimes this time in many applications, the time period or a span of space is a random variable. This time period itself is a random variable. Guys, this is very, very important. In many applications, the time period, or you can say the span of the space is a random variable. Span of the space is a random variable. For example, I can give plenty of examples out there, but one of the examples I would like to give you right now, there is the industrial engineer may be interested in modeling the time t, suppose capital T, between the arrivals at a congested intersection during the rush hour in a large city, right? I repeat, an industrial engineer may be interested in modeling a time capital T. See, he is going to model the time capital T, means that time period between some specific peak hours that will work over here as a random variable. Not the fixed time, just a random variable. Between the arrivals at a congested intersection during the rush hours in a large city. And the arrival represents the Poisson event. Whatever the traffic arrives, that is the Poisson, because Poisson is always for the discrete, but the time period itself at that time we are going to do time is a continuous, right? So time period is always a continuous thing. So time between the arrivals is a congested intersection during the rush hour in a large city. So that is the best example for the connection between the Poisson distribution and the exponential, or you can say the gamma distribution. Okay, guys, and then after, if you go through this one, this is the Poisson distribution. You know this thing is a definition, and if you take suppose x is equal to 0, you're going to get this exponential distribution. So that's how it works, because my x is equal, if you take x is equal to 0, exponential distribution like this, and x greater than or equal to x, e to the power negative lambda x, right? Lambda t or lambda x. Here it is t, so that's why we have a variable t. If it is variable x, it is like this. And suppose your x lies between 0 and x, it is 1 minus e to the power negative, because x greater than is this one, less than 1 minus this one. We can write something like this. And in order that many recognize the presence of the exponential distribution, we differentiate the cumulative distribution function to obtain the density function, so cumulative distribution function to obtain the density function that is given in this form. Fx is equal to lambda e to the power negative lambda x. Lambda e to the power negative lambda x, which is the density function for the exponential distribution with lambda is equal to 1 over beta. You can write lambda is equal to 1 over beta. If you write this lambda equal to 1 over beta, you're going to get exactly same as whatever I explained to you on the previous page, that is the exponential distribution. So lambda e to the power negative lambda x, if 1 over beta equal to lambda if you take. Okay, guys. An application of the exponential and gamma distribution now. So please notice that the mean of the exponential distribution is the parameter beta, because exponential distribution, just now I told you, look at over here, the mean is just the parameter beta. The reciprocal of the parameter is a Poisson distribution. If you take this reciprocal 1 over beta, so that is the Poisson distribution. Very important thing, guys. Please keep this thing in mind. The reciprocal of the parameter in the Poisson distribution, that is this beta. So we should always recall that it is often said the Poisson distribution has no memory. Poisson distribution has no memory, implying that occurrence in successive time period are independent, right? No memory means successive time period, they are independent. The important parameter beta is the mean time between the events. The important parameter beta is the mean time between the events. So please keep this thing in mind. And in reliability theory, where equipment failure often conforms to this Poisson process, beta is called the mean time between the failures. So this beta actually in physical way, it represents the mean time between the failures. If you want, I can repeat the same thing. It says that the mean of the exponential distribution is the parameter beta, the reciprocal of the parameter in a Poisson distribution. And we always recall that it is often said that the Poisson distribution has no memory. And because it has no memory, it implies that occurrence in a successive time period are independent. Occurrence in successive time periods, they are independent. And the important parameter beta is the mean time between the events. And this beta is the mean time between failures. Right, guys? So please keep this thing in mind. And now I would like to start with some examples, because I just gave you the brief outline about the beta and gamma function, the relationship between the Poisson distribution. And now let's start with this one. So let me continue with this one. Just look at this example number 6.17. It says that suppose that a system contains a certain type of component whose time in years to failure is given by t. To failure, the system contains a certain type of components, right? And that is in failure, right? Whose time in years to failure is given by t. The random variable t is modeled nicely by the exponential distribution with mean time to failure beta equal to 5. The random variable t is modeled nicely by the exponential distribution with the c random variable t. This t is a random variable, right? Exponential or gamma distribution, you can say. But failure beta is equal to 5. If 5 of these components are installed in different system, right? 5 of these components, they are installed, some chips, suppose they are installed in some different system. What is the probability that at least 2 are still functioning at the end of 8 years? See, at least 2 are still functioning at the end of 8 years. End of 8 years, it means first one, 0 to 8, that is nothing but your time period. That is your random variable. 0 to 8 is your random variable. So that is, you can say exponential function or like this, 0 to 8, right? In which you can say that your at least 2 are still functioning. At least 2 are still functioning. So 2, 3, 4, these components are, you cannot say 1.5 components. You can say either 1 or 2 or 3 like this. So that means that's a Poisson parameter, right? Poisson function, Poisson process, right? Just like in peak hours, suppose 5 to 7, how many vehicles are entering to that particular intersection, right? Conjunction intersection. So this number of vehicles, they are the discrete numbers, and that's why it's a Poisson process. But the time period at the same time, that is nothing but the continuous random variable. So density function is defined with respect to time, and that's why it's a relationship between the exponential function and the Poisson distribution. Very important thing, guys. Please try to keep this in mind. Okay, so let me solve this example. Very frequently we are taking help over here, help of binomial distribution here too. So let me start with this one. So let me share my whiteboard. Let me stop sharing this one and let me share my whiteboard. My whiteboard is over here, and the example that is now with you, let me just, the example, right? So I don't want to repeat the same thing. Example 6.17, page number 197 of your book. Okay, so it says that suppose that the system contains a certain type of component whose time in years to failure is given by t. The random variable t is modeled nicely by the exponential distribution with the mean time of failure beta equal to 5. Mean time of failure, that is considered as beta. You know this thing. Just now I told you beta is nothing but the mean time between the failure. Mean time between the failure. Okay, so beta is equal to 5. That is the mean time of failure. I would say mean time of failure beta is equal to 5. This mean word I have used over here because that shows that's exponential distribution. Exponential distribution, because beta nu equal to beta equal to mean for the exponential distribution. If 5 of these components are installed in different systems, what is the probability that at least 2 are still functioning at the end of 8 years, right? So let me start with the solution. The probability that the given component is still functioning after 8 years, let me write down like this: the probability that a given component is still functioning after 8 years, is given by probability of t greater than 8, right? Still functioning after 8 years, t greater than 8. That is equal to, how can you find this one, guys? That is equal to, I want to find this one. So first of all, I have to have my density function. So let me solve first of all my function. So my f of by exponential distribution, the density function by exponential distribution, the density function is given by fxb. You know this thing. Let me just write down the definition for you. That is actually not required. 1 over beta and e to the power negative x divided by beta, x greater than 0. Otherwise, you know that is 0. Okay. Right? If you want, I can write that part too. Otherwise, it is 0. Not actually required. So probability of probability of capital X greater than X, that is equal to 1 over beta and integration over X e to the power negative X by beta and dx. Good. So that is my probability of X greater than 8, right? That is equal to 1 over beta, that is equal to 5. And here it is X. X is my 8 and more than 8. So 8 to infinity e to the power negative of, I would like to write in terms of not X, but I would like to write in terms of T. So let me write this is simply T, because my X is nothing but my time period. So because of the time, I would like to write T. So here also I'm going to change my variable. Instead of dx, I'm going to write dt. So here it is negative T, and beta equal to 5, and here it is dt. So time is T, time T, right? So that's what I have over here. So I'm going to write that is equal to 1/5 and integration 8 to infinity e to the power negative T over 5 and the dt. And if you take the integration of this one, 1/5 and e to the power negative T over 5 divided by negative 1/5. So this 1/5 and 1/5 will get cancel out. And here it is 8 to infinity. And you know this thing, this is the improper integral. So if you want, you can write limit b tends to infinity, and here it is b, or you can work it directly also. So you're going to get that is equal to, here negative sign is out, and 1 over e to the power T over 5. And here it is 8 to infinity, and here it is limit b tends to infinity if you want. So then in that case, it will be b over here. If you have something like this, in that case, negative e to the power b. So let me write that is equal to 1 over e to the power b over 5 minus 1 over e to the power 8 divided by 5, and b tends to infinity. So this is infinity. Infinity divided by 5 is infinity. E to the power infinity is infinity. 1 over infinity is 0. So whole part is 0. This negative will be positive. So it is nothing but 1 over e to the power 8 divided by 5. If you use your calculator, exponential function divided by 5. So you're going to get that is equal to approximately 0.22211. So let me write 0.2. So that is equal to 0.2. So then after, let me just go other side. I'm not done so far. So now this side, we have, let X represent the number of component functioning after Tx. Let X be, or X represent the number of components functioning after 8 years. After 8 years. Then using the binomial distribution, then by binomial distribution, what we have? Yes, X be the number of component functioning after 8 years. How many components are there? 2. At least 2, means 2 or more. So my X greater than or equal to 2, if you read the example. And that is equal to summation b, then x, then n, that is equal to 5, and my probability, that is equal to 0.2, right? And my x runs from 2 to, how many components are there? 5. So 2 to 5. So that is equivalent to say that summation 1 minus x is equal to 0 to 1 and b x, and here it is 5 and 0.2. And if you use this one, if you use your binomial distribution table on the back of the book, that is 0.7373, and that is equal to 0.2627. That must be your answer. So there are exercises of this type of problems there are some problems in our exercise too, which we are going to look at after some time. Okay, guys, and now I would like to go for the memoryless property and its effect on the exponential distribution, right? So we don't have any memoryless, any kind of memory now. So memoryless property and its effect on the distribution. That's what we are going to see. 2, 3, 4 examples based on this one. And then after we will talk a little bit about the chi-square distribution. Of course, beta distribution also along the same line. And then after we will be switching over for the exercise problems. And that will be the end of today's class. Okay, so let me save this one. And let me stop sharing this one and let me share again my book. It says that this example we have done, and now we are going to go for the next part. Again, if you look at this one, again, I don't want to go through the complete all these stuffs, but the important things which I would like to discuss with you is the second part. The importance of the gamma distribution lies in the fact that it defines a family of which other distributions are special cases. But the gamma itself has an important application in waiting time and reliability theory. The importance of the gamma distribution lies in the fact that it defines a family of other small distributions like exponential and like this. But gamma itself has its own applications too. Whereas but the gamma itself has important applications in waiting time, the reliability theory. Whereas the exponential distribution describes the time until the occurrence of a poison event, time until the occurrence of poison event. Whenever poison events are there at that time, usually you can go for the exponential distribution. I repeat, the exponential distribution describes the time until the occurrence of a poison event. Poison event, I'm going to say that some time between poison events or the time or the space occurring until a specified number of poison, means specified number means discrete numbers of poison events occur in random variables whose density function is described by the gamma distribution, because gamma is a continuous distribution. So density function is given in terms of gamma distribution. And thus it becomes easy to understand that when alpha is equal to 1, alpha equal to 1 means in gamma distribution means exponential distribution. The special case of the exponential distribution occurs. The gamma density can be developed from its relationship to the Poisson distribution, the Poisson process, in much the same manner as we develop the exponential density function. That's fine. Let's go for the next example. My next example says that, suppose that the telephone calls arriving at a particular switchboard follow a Poisson process, because telephone call comes in terms of 1, 2, 3, 4 like this. So discrete numbers are there. So discrete process, that's why the Poisson process. With the average of 5 calls, your mean value, nu equal to beta equal to 5 is given to you. 5 calls coming per minute, right? Coming per minute. Every minute you have 5 calls, it's just one minute. That means Poisson distribution. What is the probability that up to a minute, now look at here, starting from 0 to 1 minute, up to a minute will elapse by the time 2 calls have coming into the switchboard, right? Now this time is a continuous random variable. Look at the second line. What is the probability that up to a minute will elapse by the time 2 calls, right? By the time 2 calls have come into the switchboard. So Poisson process applies over here until 2 Poisson events following the gamma distribution, and beta is equal to, this is gamma distribution, right? So gamma distribution, that means here it is 5 calls. So naturally my beta is nothing but beta is equal to, nu is equal to, okay, so beta is equal to 1/5, right? So beta is equal to 1/5, and 2 calls means my alpha is equal to 2. My alpha is equal to 2. Average of 5 calls per minute. 5 calls per minute means beta is equal to 1/5, right? Per minute, so 1/5. Okay, so beta is equal to 1/5, alpha is equal to 2. If you plug this value in the distribution, so you're going to get 1 over beta square x into the power of this one. Beta distribution, that is 1 over beta to the power alpha gamma alpha. Let me solve this example for you, because here it's written directly and probably you will be confused. You will get confused reading this line. So let me solve this one for you. So let me again stop sharing with this one with you, and let me go for my whiteboard so that you will have some more idea about this thing. It's not that difficult. So let me just write in a same line. Probably that is helpful to us, because I don't want to miss any of the things. So if you suppose make some different colors, then I would say that my beta is equal to, here in example 6.18. So 6.18, my beta is equal to, because 5 calls per minute, so 1/5, and my alpha is equal to 2. Alpha is equal to 2. You know this thing that my density function is given by f of x alpha beta, and that is equal to 1 over beta to the power alpha and gamma alpha, right? Into x to the power alpha minus 1. So x to the power alpha minus 1 and e to the power negative x by beta. Now, if you plug over here, suppose f of x and alpha is 2 and beta is 1/5, that is equal to 1 over beta to the power alpha. So 1 over 1/5 and square. So it is 25 over here. Gamma of 2. Now you know this thing at gamma of 2, that is equal to 1 times 1 or 1 factorial, you can say. And 1 factorial is simply 1. So no need to write, it's simply 1. And here it is x to the power alpha minus 1. Alpha is equal to 2 minus 1, that is equal to 1. And e to the power negative x by beta. Beta is equal to 1/5. So that is equal to 1/5. So it is 5x. Right, negative of 5x. That means ultimately I'm going to get that is equal to 25x e to the power negative of 5x. 25x e to the power negative of 5x. And my probability will be over here. Let me just write down here in other space. Just look at my blue lines. That's a continuation over here. So my probability that x less than or equal to 1, x less than or equal to 1, that is equal to integration 0 to 1, and my density function fx is this one. So my density function is 1 over beta square. So naturally I can write directly, right? So it is 25 because beta square already we figured it out, 25 into gamma 2 is just 1, x to the power, this is my x to the power 2 minus 1. 2 minus 1, that is equal to 1. So that is equal to x e to the power negative of 5x. Negative of 5x and dx. 25 is constant, I can pull it out. So 25 is over here. So that is equal to 25. And if you go for integration by parts, you're going to get this is my u and this is my v. So you are going to get that is equal to x as it is and e to the power negative 5x divided by negative 5 minus, right guys, minus derivative of x is 1 and integration of negative of 5x divided by negative 5 and dx. And if you open this one, you're going to get some value and that is equal to, this part will be just 1, e to the power 0 is 1 and e to the power negative 5 and 1 plus 5 and that is equal to 0.96. So that must be your answer. The probability is 0.96. So that's how you can, that's where you can solve the examples based on this one. I'm sorry guys, just write down on one board, but next time onwards, I'm going to write on the second board. Let me just save this page and let me erase this part too. So clear the drawings and let's go for the next one. My next example. Now we are going to see some example based on incomplete gamma function. This is really important. Just read the example first and then after we are going to use the whiteboard for the incomplete gamma function. Let me switch on the lights, just wait. Okay guys, so my next example says that a biomedical study, in a biomedical study with rats, a dose response investigation is used to determine the effect of the dose of a toxicant on their survival time. The toxicant is one that is frequently discharged into the atmosphere from jet fuel. From a certain dose of the toxicant, the study determined that the survival time in weeks has a gamma distribution with alpha equal to 5 and beta equal to 10. Just keep in mind this thing because nu equal to alpha times beta. So if you multiply this one 10 into 5, that is equal to 50. That is your average, your mean value. What is the probability that a rat survives no longer than 60 weeks? No longer than 60 weeks. It's simple. Rat survive no longer than 60 weeks. Just keep this thing in mind and let me just stop sharing this one and let's start with my whiteboard. Okay, so this example 6.19 says that, let x be the random variable, the survival time. Let the random variable x be the survival. Let x, or you can say let the random variable x be the survival time. Let the random variable x be the survival time. right? Or time to death. So required probability is the required probability is probability of x less than or equal to 60, that is equal to 1 over, yes, now let me just write it down. My alpha is given to us, alpha is equal to 5 and beta is equal to 10. Alpha equal to 5 and beta equal to 10. Okay, sounds good. So beta to the power alpha, so beta to the power alpha and integration 0 to 60 and x to the power alpha minus 1, right guys? X to the power alpha minus 1. Let me just go for gamma alpha. Gamma alpha is nothing but gamma of, you can write that one also outside. So gamma of alpha is equal to, okay, let me write the formula. I think that is always good. And x to the power alpha minus 1 and e to the power negative x by beta and dx, right? Density function with this one. Okay. So if you plug the values, you're going to get that is equal to 1 over beta is beta to the power 5 and gamma 5, that is equal to 4 factorial. 4 factorial integration 0 to 60. X is nothing but x to the power alpha minus 1. Alpha is equal to 5, right? X to the power alpha minus 1. Okay, let me write this one because I would like to let you know that what we mean by the incomplete gamma function over here in this particular example, and e to the power negative x by beta. So I don't plug the value of beta since the beginning. Look at over here, because I just would like to use some substitution for my incomplete gamma function. And here it is dx. Here it is dx. Okay, so now whatever I have, my x by beta, I would like to consider that as some substitution that is equal to, suppose, some y. So I would like to say that y is equal to x by beta. So this y is equal to x by beta. So taking y is equal to x by beta, I have dy is equal to 1 over beta times dx, or dx is equal to, or you can say dx is equal to beta dy. If you use this one over here, you're going to get that is equal to 1 over beta to the power 5, right? Beta to the power 5. Gamma 5 is constant. It will not be changed. These are the values in terms of x. So if I take, suppose x is equal to 0, right? My y equal to 0. So integration y is equal to 0. And x is equal to, suppose, 60, and beta is already given to you, that is equal to 10. So it is 6. So y is equal to 6. And x to the power alpha minus 1. So I would like to write x is nothing but my y times beta. So y times beta to the power alpha minus 1. And here I can write that is equal to e to the power negative y, and dx is nothing but dx is equal to beta times dy. Beta times dy. Here I wrote it down beta to the power 5, but I just want to work with alpha because I know alpha is equal to 5, but here this is the formula. So let me just use, just for the sake of convenience, I don't want to plug any value. So let me use alpha equal to 5. We know this thing, alpha equal to 5. That is equal to, now you can see here that is equal to integration. Let me just use the eraser. Okay, so 1 over beta to the power alpha, gamma alpha, this beta to the power alpha minus 1, and this beta to the power 1, so plus 1, that is beta to the power alpha. This alpha and this one will get cancelled out. Integration, you're going to get y to the power alpha minus 1 and y to the power alpha, e to the power negative of y and dy, and gamma is this one. Now if you want, you can plug the value that is equal to gamma of 5 and integration y is equal to 0 to 60. So y is equal to 0 to 60 and y to the power alpha minus 1, that is equal to 4. Alpha minus 1 is equal to 4 and e to the power negative y and dy. And now you can see this one, that is nothing but what is this? This is nothing but my, this is alpha equal to this one, right? Alpha equal to 5. So you can write f of 6 is the range beta. So that is equal to 6. My x value is 6 and my alpha. So it is x alpha like this. Fx alpha is equal to 5. So that is equal to 5. If you use the table, I think A23, almost at the end of the book, A23 is clearly given this value, X values, and then after you can say your alpha values. So 6 and 5, that corresponds to 0.715. So that is your answer, 0.715. So whenever you have the incomplete gamma distribution, something like this, right? The integral above, this is this integral that was based on the incomplete, that is to the use of incomplete gamma function. Incomplete gamma function is not ready-madely given to you in the exact definition of the gamma function, but we have to use some substitution to get the integration. And that's the way, that's the reason why it is called the incomplete gamma function. So it's not exactly the gamma function, but we have to use some substitution to convert that one in terms of the gamma function like this. And that's the reason it is called the incomplete gamma function. So just keep this thing in mind. We will solve some other examples too based on the same one. Okay, guys, now I would like to, let me just save this one. I would like to go for the another part. So let me stop sharing this one and let me start sharing the book again. My next example says that I just would like to go for two more examples. One example is based on this gamma function. Second example is based on the exponential function. And then we'll start the chi distribution and the examples. This one is really good because whatever I'm saying, it's really very easy because whatever we have done is just a repetition. It says that, right now I'm talking about this example. It is known that from previous data that the length of time in months between customer complaints about a certain product is a gamma distribution with alpha equal to 2 and beta equal to 4. Alpha equal to 2, beta equal to 4. Changes were made to tighten quality control requirements. Following these changes, 20 months passed before the first complaint. First complaint and then 20 months passed, there is no any more complaint. Does it appear as if the quality control tightening was effective? Whatever the quality control tightening is effective, if this is the scenario that alpha equal to beta equal to 4 and there is no complaint from first to 20 months. Let's see. So X with the time, again, let X be the random variable. Let the random variable X represent the time of the first complaint, right? Time to the first complaint, which under the condition prior to the changes, followed the gamma distribution alpha equal to beta equal to 4. The question centers around X greater than or equal to 20, right? 20 months and more, X greater than or equal to 20 is given. X greater than or equal to 20, that means you have to write something like this, that 1 minus probability of X strictly less than 20, and strictly less than 20, but here your density function that is in terms of gamma function. So 1 over beta to the power alpha gamma alpha integration X to the power alpha minus 1 and e to the power negative X by beta and gamma alpha. Gamma alpha, usually people write gamma alpha inside. You can, if it is constant, you can write it down outside too. It is always constant. But here also you can see that X by beta, because your beta is something different. So you need to write X by beta. This is again the problem of incomplete gamma distribution. So you can write X by beta that is equal to Y. X by beta is equal to Y. And whatever we did in the previous example, exactly follow the same pattern. Exactly follow the same pattern to get rid of this integral sign. So X greater than or equal to 20, 1 minus integration 0 to 5. And if you write this as X by beta equal to Y, you're going to get this distribution. I mean, this function. And finally here 5, that is your X value, and your alpha is 2. So you can write F alpha X and alpha. So X5 to again go for table A23, and you're going to get this value. So that is equal to this one. So as a result, we can say that we can conclude. You can see over here F52 is for this one. Okay, so 0.04. It's a very less probability, guys. Look at over here, very less probability, right? 1 probability and 0.04 is extremely nearer to 0. So as a result, we could conclude that the condition of the gamma distribution with alpha equal to 2 and beta equal to 4 are not supported by the data that an observed time to complain is as large as 20 months, right? Observed time to complain. observed time to complaint is as large as 20 months. Thus, it is reasonable to conclude that the quality control work was effective. Quality control work was effective. And my last example that is based on the exponential function. If you consider example 3.31 on page 94, long back, chapter number 3, but let me just go for this example, because we are mainly interested in density function. So we use this function on page 94. Okay, so accept this one, 1/4 e to the power negative y by 4. It's an exponential function. Look at over here, 1/4 e to the power negative y/4, right? And not that y is the exponential random variable with nu equal to 4 years. The machine is considered a bargain if it is unlikely to require a major repair before the 6th year. What is the probability? 6th year. What is the probability? Means more than 6. Y greater than 6. What is the probability that the major repair is required in the 1st year? Right? First year means in the 1st year means anytime in the 1st year. Probability x less than 1 or y less than 1. So first of all, my exponential function 1 over beta e to the power negative t by beta dt, right? T by beta dt. You take the integration and you are going to get the function like this. Just I figured it out, my density function, exponential distribution, a density function fy equal to, this is my density function. So exponential distribution is this one. Now probability is y greater than 6. My first question, that is 1 minus probability of y less than 6. Y less than 6 means it is 1 minus f of 6, right? Y less than 6. So if you replace this x by 6, 0 to 6, right? So y less than 6 means 0 to 6. So 0 to 6, you're going to get this is the answer. And y less than 1, again the same thing, 1 minus e to the power. If you take here 1, 0 to 1, you're going to get negative 1/4. Right? Because beta is equal to 4. Nu equal to 4 means beta equal to 4, because exponential function mean is nu equal to beta. So beta equal to 4. So let me write beta equal to 4 over here, and here also you can write beta equal to 4, and you are getting this as the answer. The last part of this one is the chi distribution. The chi distribution, that is, you can see another very important special case of the gamma distribution obtained by letting whatever we have in gamma distribution, not the exponential, because we are using alpha and beta both. So alpha equal to some v by 2, some function v by 2, and beta equal to constant 2, where v is a positive integer. It could be 1, 2, 3, 4, 5, anything. The result is called the chi-square distribution. And this distribution has a single parameter v called the degree of freedom. This v is the degree of freedom. You can see everything that is in terms of v now, because now beta equal to 2 and alpha equal to v by 2. So everything that is in terms of v. Right, so this is called the chi-square distribution with v as a degree of freedom. And for chi-square distribution, again, my nu equal to v and my mean equal to v, and my variance is nothing but sigma square, that is equal to 2v. Variance equal to 2v. And the last distribution, that's a beta distribution. For beta distribution, first of all, let me define beta function. Definition of beta function is very well known to all of us, because we went through this one probably in 11th, 12th grade. I'm not sure, but usually people go through this one in statistics, elementary statistic course. So beta alpha beta is equal to 0 to infinity x to the power alpha minus 1 and 1 minus x to the power beta minus 1. That's the definition. X to the power alpha minus 1, 1 minus x to the power beta minus 1. And you can convert this one in terms of gamma function, that is gamma alpha gamma beta over gamma alpha plus beta. So beta alpha plus beta, usually people don't write this one, because gamma, this is really very easy to calculate. Gamma n equal to n minus 1 factorial, like this. So people, this is the definition, of course, that x to the power alpha minus 1 and 1 minus x to the power beta minus 1. But that is ended up with gamma alpha gamma beta times gamma alpha plus beta. Right, and the density function beta distribution, this is beta function, right? And the beta distribution that is given like fx is equal to density function for beta distribution, 1 over beta alpha plus alpha beta, the same thing, beta alpha beta, x to the power alpha minus 1, 1 minus x. See here, just remove this one, remove this equality sign, beta alpha beta, divide by this one, and x to the power alpha minus 1, 1 minus x to the power beta minus 1. That is my density function. And the mean over here, that is equal to alpha over alpha plus 1 and variance is sigma square equal to alpha beta over alpha plus beta square, alpha plus beta plus 1. But again, see, and then after we have log normal distribution, we are not going to do this thing because there's the course for this is the same thing you're going to learn in the next statistic course. So let me drop this part too. Variable distribution, exactly same over here. Let me stop this part too. And some failure, some interpretation of the failure rates and like this, that's fine. That is for the variable distribution. And let's start with some examples. So I would like to again go back. Let's read the example, and then after I would like to go back to what we say. I would like to go back to the whiteboard and solve the examples. I would like to go through 2 examples simultaneously because I don't want to go for back and forth book and whiteboard. So just read these 2 examples. Example number which you want me to take, 41 and 42, I think so. That's the right thing. If a random variable x has the gamma distribution with alpha equal to 2 and beta equal to 1, find p between 1.8 and 2.4, right? Alpha equal to 2, beta equal to 1, gamma distribution, everything is provided to you. So we will do this thing. Probability of this one, that is equal to 1 over beta square, right? Beta to the power alpha, right, guys? So that is equal to, yes. So beta is equal to, here is simply 1. So I think that is more easy. While beta is simply 1, it should be something different. Beta equal to 1, that makes your example very simple. If you have, suppose, let me take beta equal to 2 or 3. Let's take beta equal to 3. That is more useful because beta equal to 1, just a particular case of that example. So we'll take beta equal to 3, alpha equal to 2. That will give you more idea. Example 6.42 says that, suppose that the time in hours required to repair a heat pump is a random variable x having a gamma distribution with the parameter alpha equal to 2 and beta equal to half. What is the probability that on the next service call, at most 1 hour will be required to repair the pump? At most 1 hour. At the most 1 hour, not more than 1 hour. So probability of x less than 1 or equal to 1. At least 2 hours will be required to repair the heat pump. At least 2 hours, right? At least 2 hours means 2 or more than 2. So 2x greater than or equal to 2. So that's what we are going to find over here. In first example, alpha equal to 2, beta equal to, as I told you, 3, 1.8 to 2.4. Second example, alpha equal to 2, beta equal to half. And at the most 1, at least 2. Okay, so let's go for the whiteboard. So my first example number, I would say 6.41. 6.41, it says that my alpha equal to 2 and beta equal to 3. In your book, it is given 1, but we are taking 3. And find the probability of 1.8 is less than x is less than, of course, here you have to have capital X, is less than 2.4. Okay, sounds good. 2.4. And that is equal to, yes, guys, so that is equal to, just plug the values. That is equal to integration. If you want, you can take 2 or 3, whatever you want to say. If it is 1, then sounds good to me also. I don't mind. If you want to take 1, that's also good. Anyway, so that is equal to integration 1.8 to 2.4. And here I have, yes, please, x to the power alpha minus 1, right? So x to the power alpha minus 1, and e to the power negative x by beta. So that is equal to 1.8 to 2.4 x to the power alpha minus 1, 2 minus 1, that is equal to 1, and e to the power negative x, beta is equal to 1. Beta is equal to 1 and dx. So that is equal to, just go for the term by term integration. I mean to say that, sorry. Integration by parts. So this is my u and this is my v. So x as it is, e to the power negative x and negative 1, and 1.8 to 2.4 minus under sign of integral. It is by parts, right? By parts. L-I-A-T-E, exponential function stands last. So that is my v. And here it is derivative of x is 1. So derivative of x is 1 and integration e to the power negative divided by negative 1 and dx. And bracket complete. So that is equal to, if you open this one, you're going to get negative x e to the power negative x minus here integration of e to the power, this negative positive e to the power negative x is negative e to the power negative x. And here you have 1.8 to 2.4. And that is equal to whatever the value is. Just use second fundamental of theorem of calculus. Whatever you're going to get, that is your answer. Here, my answer is 1.1545, right? And then after, I would like to go for the second example. As I told you, that is 6.42. Second example is 6.42. says that, as I told you, alpha equal to 2, beta is equal to 1 by 2, so 1 by 2, and beta equal to 1 by 2. At most 1 hour will be required to repair the pump. Okay, so probability of x less than 1 is equal to okay, probability of x less than 1 and 1 over beta. Beta is equal to beta square, right? It is 1 over beta square. Formula says 1 over beta square. So 1 over beta square is 1 by 2 and square is 1 by 4. So it is 4. So it is 4 outside. Integration and gamma 2 equal to just 1 factorial. No need to write. Integration 0 to 1. And here it is x to the power alpha minus 1. 2 minus 1 is simply 1. And here it is e to the power negative of x by beta. Beta is equal to 1 by 2. So 2x and dx. Again, the same thing, guys. Just use the integration in by parts. So here it is u and here it is v. If you use this, I'm going to get that is equal to 4 and negative 2x e to the power negative 2x. Let me just take some liberty to write it down very quickly because you know this thing. That is equal to 0 to 1 and 1 minus it is 0 and 1 minus e and e to the power negative 2, and that is equal to something whatever you are going to get. I have 5940, so that is the answer for A part. The B part says that probability of x greater than 2. So that is equal to exactly same thing 4, but now here it is 2 to infinity and my function remains the same, e to the power negative 2x and dx, and that is equal to negative 2x e to the power negative 2x minus e to the power negative 2x, and my range is 2 to infinity. Just plug the values and whatever you're going to get, that is your answer. So that's how you can solve these two examples. Let me save this file again, and then after I would like to go for the next example. So my next example is something like this. Setting the book. And next example, I think let's go for example 6.45. Just 2 more examples and we'll stop. 6.45 because I think 6.50, that is the beta distribution. 6.50, get over here. Clearly everything is mentioned is the beta distribution. So just use the beta distribution and try to find the density function, integrate it and get the answer. Same over here. 6.45 is a nice example. So let me go through this one, 6.45. The length of time for one individual to be served at a cafeteria is a random variable having an exponential distribution with a mean of 4 minutes. Mean is 4 minutes. What is the probability that a person is served in less than 3 minutes on at least 4 of next 6 days? Okay, at least 4 of next 6, so 0 to 6 days. Out of these 6 days, at least 4 of next 6 days, the person is served, right? The person is served in less than 3 minutes. Person is served in less than 3 minutes. Less than 3 minutes means 0 to 3. That is your continuous random variable, right? That is your exponential function. 0 to 3, that is your exponential function. So I can start something like this. And what is the probability that, less than 3 minutes, at least 4 of the next 6 days. Okay. Let's again start with this one. I already save this file. So let me save this one. And now let me erase, let me clear everything. Clear. And now let's start with this one. Okay. So it says that 6.45 probability of x less than 3, capital X, of course, less than 3, that is equal to, of course, it is 1. Let me write directly now, because mean, you know that exponential distribution means mean equal to beta equal to, here it is given 4 minutes. 4 minutes. So 1/4 mean equal to 1/4 integration 0 to 3 e to the power negative x by 4, right? Beta equal to 4 into dx. And that is equal to, very simple, because e to the power negative x by 4 and negative 1/4. And here it is 0 to 3 and 1/4. So this 1/4 and 1/4 will get cancelled out, and negative sign out, 1 over e to the power x by 4, and here it is 0 to 3. Here it is 0 to 3. So that will be equal to, because you know it is e to the power 0 is simply 1. So 1 minus 1. So it is 1 minus e to the power negative 3/4. And if you use your calculator, you're going to get something that is your answer. Of course, it probability means it has to be between 0 to 1. Okay, now but I'm not done. This is just the probability, right? Now let's start it like this. Let capital Y be the number of days, let capital Y be the number of days a person is served in less than 3 minutes. In less than 3 minutes. Then what will happen? Then probability of y greater than or equal to 4, right? Greater than or equal to 4, because 6 out of 4 days. So y greater than or equal to 4, that is equal to, guys, please pay attention over here. That is equal to x is equal to 4 to 6. And my binomial distribution, random variable y, my total outcome, that is equal to 6. And my probability. My probability already I figured it out. Here the probability is 0.5276. 0.5276. So 0.5276, right? So that is equal to, I can write 64, 0.5276 to the power 4 and 0.56 to the power 4. Right, guys? So my probability and my Q. This is my P and this is my 1 minus P, that is equal to Q. So 1 minus this one is equal to 0.4724. I think so. And square plus 63, 0.5276 cube and 0.4724 plus 62, 0.5276, here power 1 and here power 0 square, and here it is 0. No need to write, right? And if you use your calculator, you're going to get one number. That number is 0.3968. So that is your answer. So that's how you can solve the example based on this one. And now I would like to go for the last example. My last example is, before that, let me just save this file. I don't want to lose this one. Okay. And now the last example, as I told you, example number 6.50 is just the repetition. So don't worry about it. I mean, it's a beta function, so you can solve it by yourself. And I would just like to share my last example with you, and that will be the end of the chapter. Which one? Let's go for 54. Sounds good. The lifetime in weeks of a certain type of transistor is known to follow a gamma distribution with mean value 10 weeks and the standard distribution, standard deviation square root of 50. Standard deviation square root of 50 is provided to you. Look at over here. What is the probability that a transistor of this type will last at most 50 weeks? At the most 50 weeks, right, guys? So x is less than or equal to 50. That's what it means. At the most 50, right? So that is equal to 50. Okay, x is less than or equal to 50. And the second part says, what is the probability that a transistor of this type will not survive the first 10 weeks? First 10 weeks, X is less than 10, strictly less than 10. Transistor will not survive. Guys, keep in mind this thing here. You are given the mean value 10 and the standard deviation. You're not given alpha, you're not given beta, but mean value and standard deviation. Usually in the practical way, practical problems, you will be getting mean and the standard deviation. And then after you can apply whatever distribution or whatever the suitable distribution you want to use, right? So please keep this thing in mind. This is the most important example because usually practically you have this type of examples in which alpha and beta will not be provided to us because alpha and beta, they are always coming from the mean and the standard deviation or the variance. So I'm going to start like this. Just keep in mind this thing here. It is 10 and square root of 50. Right, guys? 10 and square root of 50. So just keep this thing in mind. And then after it is at the most, so strictly less than 50 and strictly less than 10. So we are going to solve this one. Okay, guys. Let me do this thing. And this is the end of this chapter. We are not going to do anything more over here. So I think yes, and this is chapter number 7, function of random variables, but that's the optional case. So we will switch over to chapter 8. Anyway, let me stop over here and let me go for my whiteboard for the last example. Example number which one? 6.54. 6.54. Pen is not, it's very light. So let me change the color. This is okay. Okay, so we are given my new value that is equal to 10 and my standard deviation that is equal to square root of 50. Standard deviation that is equal to square root of 50. Now, please keep this thing in mind. The gamma distribution is clearly mentioned in the examples. For gamma distribution, my new is nothing but alpha beta. So alpha beta is equal to 10 and my standard deviation that is given by square root of alpha beta square that is equal to square root of 50. So this is the gamma distribution, square root of 50. Alpha beta square sigma is equal to this one. Okay, now alpha and beta is equal to 10. Alpha beta square, alpha and beta is equal to 10. How can you get these values? That is important. Guys, look at over here, please. First of all, let me solve like this. I have sigma square is equal to alpha beta square, and that is equal to 50. And I am given that alpha beta is equal to 10 and alpha is equal to 10 divided by beta. 10 divided by beta. If I go back and plug this value over here, I'm going to get 10 divided by beta and beta square that is equal to 50. This beta and this will get cancelled out. So my beta is equal to simply 5. My beta is equal to 5. See, I found my beta. If you go back and plug this value of alpha and beta somewhere over here, or if you want, you can plug either here, whatever you want to use. So since I would say alpha beta is equal to 10, so naturally my alpha equal to beta 10 divided by beta, that is equal to 10 divided by 5, and that is equal to 2. So my alpha is equal to 2. Alpha equal to 2. Beta and alpha once we found, then after I can find that my sigma is nothing but if you want, otherwise actually it's not required. Okay, so my A part says that using the integration by parts, I can say x is less than or equal to 50. That is equal to 1 over beta to the power alpha and gamma alpha, and integration 0 to 50 and x to the power alpha minus 1 and e to the power negative x by beta and dx, x by beta and dx. So that is equal to 1 over 25, right? Why 1 over 25? Because alpha equal to 2 and beta equal to 5. 5 square is 25. Gamma 2 is just 1 factorial, no need to write. And then after integration 0 to 50, and here it is x and e to the power negative x by 5, and here it is dx. Again, if you use integration by parts, this is my u and this is my v, you're going to get 1 over 25. And here it is x e to the power negative x over 5 divided by negative 1/5 minus under the sign of integral e to the power negative x over 5 and negative 1/5 and dx. You can pull this one out. So here it is 5. Here it is 5, and just go for the integration of this one. So 0 to 50. And finally, you're going to get one answer, 0.9995, something like this. So this is my A part. My B part says that probability of x less than 10, and that is equal to 1 over beta to the power alpha gamma alpha, and that is equal to integration 0 to 10 x to the power alpha minus 1 and e to the power negative x by beta. So here you have to use the incomplete integration because you are not getting, so x by beta is equal to y. So put x by beta is equal to y. So dx is equal to beta times dy. If you use this one, you're going to get that is equal to p of x less than 10. That is equivalent to say that py less than 2. Agree? Because x is equal to beta equal to 5, x less than 10, 10 divided 5, y equal to 2. So y equal to 2. And that is equal to integration y, range of y from 0 to 2 and y e to the power negative y dy. Just use by parts and you're going to get some answer 5940. So that is the end of this chapter, guys. And rest of the examples, just use the definition and solve by your own. So I think we did things over here. So let me stop sharing this one. Thank you so much. Let me save this file. Okay, guys, and let me stop sharing this one. And I will see you next time, guys. Enjoy, just work hard. And next time we will start the new chapter, chapter number 8. Chapter 7 is just optional, so I don't want to go for this one. So chapter number 8, we're going to start next time. Okay, guys, thank you so much. Thanks for your patience. Almost it is 1 hour 15 minutes. So let me stop over here.